The major challenge facing today's industrial companies is the conversion of their energy supply to renewable energies. There are various technologies that can be used for decarbonization. The hydraulic conversion of the technical center is of crucial importance for this transformation. This film was created to show the hydraulic conversion of a factory's technical center simply and schematically. Such a step is a technical and economic prerequisite for the utilization of renewable energies. What are the most important energy criteria for the factory of the future? In addition to a CO2-free factory, demand-oriented energy procurement and distribution, security of supply, Industry 4.0, and the use of AI in Industry 5.0 are all essential. Established factories usually have technical components whose useful lifespan has long since expired. Plant expansions or changes to production technologies have disrupted the hydraulic system, which is usually oversized. Huge unnecessary volume flows are transported through the area, wasting valuable energy and causing operating costs to rise. We would like to use this example to show one way to master hydraulic conversion and the use of renewable energies. In order to achieve the goal of CO2 neutral production, the primary goal should be to reduce internal consumption. For electricity, renewable in-house generation can be installed on-site and green electricity can be purchased. The company currently sources its energy from the German electricity mix as well as from natural gas. More technical solutions are needed to replace the 37% share of energy procured from natural gas. How can this be done? In our example, we first look at the inventory, which is around 30 years old. In the field at the bottom left, you can see the natural gas consumption and the associated CO2 emissions. The plant has 3 large gas boilers. One of them is redundant. These 3 boilers supply the individual areas of the plant via a large pump and distributor, shown here schematically. Because the plant has grown over the years and new production areas as well as heating surfaces have been added, the current state no longer corresponds to the actual requirements of the heating network. This results in a hydraulic system that no longer functions properly, excessive volume flows, and the associated increase in operating costs. In this example, we want to look at the water basin of the paint shop and the ventilation system. Both are highlighted here. The simplest technical solution would be to simply replace the existing gas boilers one-to-one and continue to operate as before. However, this would not achieve any gas and CO2 savings or hydraulic improvements. Another option is to replace the old boilers with new ones that use dual gas and hydrogen burners. Although this would reduce CO2 emissions, it would quadruple operating costs, as hydrogen is still very expensive. This option also does not achieve an improvement in the hydraulics of the system. The existing gas boilers could also be replaced by high-temperature heat pumps. This also reduces CO2 emissions, but both the investment costs and the operating costs are higher than with the first option. Here too, there is no improvement in hydraulics. In order to prepare the overall system for the future, measures to reduce the heat demand are first proposed in order to then redesign the heating center according to that new reduced demand. The hot water basin of the paint shop can then be dispensed with in the future, as the new energy-optimized engineering process will manage without heat. New heat exchangers can be installed in the ventilation systems so that the cold air supply is preheated with the warm exhaust. After the test, the flow and return temperature in the entire heating network can be reduced by 20 degrees Kelvin. This leads to a significant reduction in heat losses. These 3 measures, optimized process, heat exchanger, lowered temperature, can be implemented in a first construction phase. This means that the heating circuit to the water basin of the paint shop can be dismantled and the entire heating circuit manifold can be reduced in size. By using heat transfer in the form of a heat wheel in the ventilation system, the heat requirement for heating the hall can be significantly reduced. As the process no longer requires such high temperatures, the energy requirement in the entire heating network could be reduced. This optimization results in reduced volume flows in the network, and smaller and more efficient pumps can be used. With these measures in the first construction phase, the heat requirement can already be reduced by 40%. However, one thing is crucial for all these measures: converting the hydraulics in the technical center. Having oversized or undersized components in the entire system leads to higher energy costs, as they are not used at the optimum operating point. This means that each heating circuit is recalculated and adjusted for the heat it actually requires. Thus, the size of the heat generators can be reduced and designed to meet demand. Hydraulic conversion is of crucial importance for the integration of renewable energies. There is a very big difference in investment costs between a heat pump with a capacity of 1 megawatt and one with only 0.3 megawatt after energy optimization and hydraulic conversion. Without the hydraulic conversion, an economically viable integration of renewable energies is not recommended. Following the successful conversion of the distribution system, the heat generators can then be replaced in the second construction phase. The hydraulic conversion makes it easy to integrate the heat pump into the existing system. 2 gas boilers will be dismantled first. The third gas boiler will take over the peak load and be replaced later in the third construction phase. The switch to the heat pumps results in a considerable reduction in gas consumption of approximately 85%. The amortization for the second construction phase is approximately 3 years. With the third construction phase, the heating system achieves almost complete CO2 neutrality. A second heat pump takes further operating hours away from the gas boiler. In addition, the third gas boiler can now be replaced with a modulating burner to meet demand. As a result, this gas boiler only runs for a few hours a year, as shown by the blue section on the right of the diagram. Alternatively, it can also be operated with hydrogen. Let's now compare all these results to the current conditions. Around 90% of the current gas consumption can be saved through the individual measures, the hydraulic conversion, the installation of 2 heat pumps, and the replacement of a gas boiler. That saves around 125,000 euros per year. This also illustrates the summary of the construction phases in terms of CO2 and gas savings. The highest savings are achieved in the first and second construction phases. With the third construction phase, a further step towards complete freedom from CO2 can be achieved. If you are planning the use of renewable energies in your company, we can accompany you with our comprehensive engineering expertise and many years of experience. We support you from conception to implementation and offer customized solutions for your individual requirements. Numerous successful projects and satisfied customers are the best proof of our expertise in this field. Let's shape a sustainable future together.